Afternoon, everyone, and welcome to another Safer Sim webinar. Today is February 12th, 2019, and our presentation will feature a collaborative project from the University of Iowa and the University of Wisconsin-Madison. Please use the chat box at the lower right corner for any questions or comments. We will address those when the presentation concludes. So our first presenter today is Kelvin Santiago from the University of Wisconsin-Madison.
Thank you, Jacob. Our presenters today, in addition to myself, again, my name is Kelvin Santiago, will be Yuan Yang from the California State University at San Marcos, Shumjajit Chakraborty from the University of Iowa, and Joseph Kearney from the University of Iowa also. So we're going to start a presentation with a little bit of background on the project, which will be provided to you by Joe Kearney.
Hi, this is Joe Kearney. I'm here in cold and snowy Iowa City with Shomo. The project is a collaborative project. It was meant to be a proof of concept to look at using the game engine Unity 3D as a basis to create a distributed interactive simulator connecting our pedestrian simulator in Iowa City with a driving simulator in Madison, Wisconsin. So the objective was to put the two simulators together so that a pedestrian wearing an HTC Vive head-mounted display could walk across a roadway, and at the same time a driver would see the pedestrian walking across the road in a driving simulator in Madison, Wisconsin. We were interested in using a commodity game platform, which has become increasingly used in simulation environments, to see just how well it would work and how much trouble it was put together. It comes with very powerful networking support, and so we were interested to see how far we could go with that. This builds on Yuan's PhD dissertation that connected our two pedestrian simulators in Iowa City and adds the remote possibility, the remote connection, and then also inserts a driving simulator into the loop. Next slide, please. So there's a lot of work in distributed simulation originating in military simulation work in the 1980s with SimNet. The primary focus of the military work was on military war games and in soldier training, connecting simulators around the world to train soldiers to do collaborative kinds of interactions in battlefield kinds of situations. The SimNet protocol led to distributed interactive simulation, DIS, which is now an IEEE standard, and more recently to the high-level architecture HLA for simulation that evolved in the 1990s. The focus of these standards is looking at the kind of packets that send information around and also how to deal with dead reckoning and timing of the simulators. More recently, there's been work in connected driving simulators. I think the Sawyer and Hancock was the earliest one we could find published on this. There have been a number of other recent papers on connected driving simulators and efforts to link simulators together. The pedestrian and driving simulators, we could only find one previous paper out of Germany that connected the pedestrian simulators together and used a keyboard interface to move a pedestrian and compared having an interactively controlled pedestrian with a pedestrian that was a bot or an autonomously controlled pedestrian. Next slide, please. So this is a schematic of what our connected simulator is and how it works. It's based on the Unity high-level API for connected gaming. That's a distributed gaming platform. It's a client-server kind of an architecture, and you can either have a separate server or one of the clients can be a server. So in ours, the pedestrian simulator at Iowa was the host and was both a client and a server, and it connected over the network to the driver client at the University of Wisconsin. So a little bit later, Yuan's going to pitch in and tell us a little bit more about the technical underpinnings of how HL API works. This is just meant to show you how information is communicated one to the other. You'll see on the left, there's a pedestrian who's wearing a HTC Vive head-mounted display. Their view is shown on the left-hand side. And on the right-hand side, you'll see the view for the driver. And if you look, you can see it's a little bit in the shadows, but there's a pedestrian there walking across the road. So the oncoming car on the left is the oncoming driver. And with the cursor there, Kelvin is identifying the pedestrian who's walking across the road. Now, the only information we sent across in this version was the head-mounted display position and orientation. That's tracked with SteamVR using the Lighthouse tracking system that comes with the Vive. And so that allowed us to move the pedestrian around. And as the pedestrian moved, there's automatic animation that triggers the pedestrian avatar to show some articulated motions. It's a bit crude, admittedly, but it shows you the capability and what's possible. If in a more complicated version, what we would do is motion track the pedestrian and then transfer over the motion tracking information and do more direct animation to reflect the motions of the pedestrian. So next slide. So why is Unity 3D an interesting simulation engine? It has a number of advantages. So it's flexible, it's very easy to use, it's low cost. The individual versions, students can get an individual version that they can get for free. There's a worldwide community of users. There are excellent tutorials online in order to learn about how to program and use Unity. There are a wide range of built-in components and models that you can get on the asset store, some for little or no amount of money. There's content building tools that are being developed, and there's built-in support for network-based gaming. Now, the disadvantage is that there are no integrated tools now for scenario modeling and no integrated tools for generating ambient traffic. And without a road model, if you have complex roadways with curvy, twisty, bendy roads and complex intersections, it can be a chore to program from scratch through scripting the motions of the scenario vehicles. Next slide, please. So ours was based on an asset from the asset store in Unity 3D that's called Simple City. It's a very kind of cartoonish, but provided us with a good basis for us to do the simulation. The simulation, we extended this model by having a extended road. So we built a simulator using the Simple City and had an extended road so that the driver could drive down a long road and the pedestrian then could see the oncoming car and coupled it with a scenario vehicle that went along in front of the car. Next slide, please.
Okay, so what I want to talk to you now is a little bit about the driving simulator environment that we were running at the University of Wisconsin-Madison. And what you see in here is basically just a random picture during our test in which we actually were able to just run a simulator, a Unity-based simulator from our engineering hall building and connect to Iowa and kind of see the pedestrian interacting with a driver and so on. As Joe mentioned, one of the things that we did as part of this project is actually creating a driving simulation tool using the Unity game engine, as well as some additional components for the driving simulation tool using C#. Now, in addition to just using Unity, one of the things that we did for our projects is actually try to isolate the different driving simulator components into different modules to simplify development later and do future work. For example, instead of just using the built-in tools for interacting with control system, which could have been a very simple process, we decided to provide a more robust solution, and we created our own control system that is able to plug it into different controllers. So we created a module that allows us to control a vehicle in Unity through another piece of software that other piece of software is connected to a remote controller. And later in the slides, you'll understand why that makes sense and what is the benefit of doing that as opposed to just using the plug-and-play tools that Unity provides. The other thing that we did as part of this project is created a basic, very, very simple high school physics level game engine for the driving simulator. We also created that in an isolated form, and the reason we did it in an isolated form, again, as a separate module, is to simplify, it's just future-proof the simulator tool that we created in Unity. In addition to the game engine, to the individual control that we created, we also added data collection capabilities. And while this was a demonstration project, we wanted to just do a proof of concept and show, like, yes, we can, if we need to, we could do data collection for an experiment. That means that we added data collection tools to Unity that allows us to record the position of the vehicles, the speed of the vehicles, the location of different elements, just as we would obtain with any of the traditional driving simulation tools that are available in the market. And finally, the other thing that we added, even thought we were just interacting between two agents in the simulation, we added the capability to the driving simulator to have scripted vehicles. For example, if you look at all the platforms that are out there, all of them allow you to have like a pedestrian jump in front of you, not an agent, an external agent like the one in Iowa, but just an automated artificial pedestrian jump in front of you by specifying a path. We can do the same thing with an actual vehicle. So we try to make this simulation tool a little bit closer to what we're used to seeing in the driving simulator community. That means that we also added capabilities to have like signal status display the actual signal status in a traffic engineering friendly way. We added that capability to the tool, and that's basically a description of our driving simulator environment. Again, just a Unity-based system that was heavily customized with the addition of custom modules. And now, Juan will talk to you about the Unity 3D high-level API for networking.
Hi everyone, this is Yuan from Cal State San Marcos. I graduated from UI last year, so I was working on this project last year. For Unity programming, you would need to think about gaming, so like multi-people gaming over the internet. So instead of the regular simulation that you would see, for example, pedestrian simulation would have a different code that is directly only for pedestrian, and driving simulator would have a code for driving simulator. So it's different from that model. When we code with Unity, everybody would actually use the same copy of the code. Just like the online gaming, every player would download the same copy of the game. So that's kind of the feature of Unity network gaming programming. And also there would be two types of game network programming that we can do. One is the high level, one is the low level. The low level is similar to the regular simulation programming with sockets and UDP, TCP, whatever things that we use. But the high level is a more convenient packaged model that we can use to program the Connect simulation for using Unity. So it also has a client server architecture, but it's just one of the players serves as the server, and also the same copy would have a client on it. So everybody would have the same copy of the code. And so it basically can be done by using a drag and drop manner. But using the typical Unity gaming programming drag and drop, we would be able to connect up like the player of the same type, for example, to pedestrians or to drivers. To mix up the pedestrian and the driver, we need to actually modify the built-in network manager a little bit, so we can put one side as a pedestrian player, one side as a driver player. And then on each side of the code, we'll just figure out whether we're running as a pedestrian or whether our player is a driver, and use that variable to figure out which camera to where should we put the camera, whether we should move the pedestrian or just move the car. And also with the coding, after we code the simulation, we are also interested in looking at the runtime delay because we are running the simulation one node in Iowa and one node in UW. So we want to figure out about the simulation round trip time. And we did a few round trip timing tests, and the result came back at about round trip 200 milliseconds. So one-way simulation delay would be 100 milliseconds. And that's including all the network delay and also all the rendering delay. So that would be if we press a key on UI, and then the whole movement would show up inside of the UW simulation. So that's the timing that we did. So that would be high-level API. If you're interested in the technical details or the tricks that we did to do the timing test, you could ask after the talk. Okay, next slide.
So this is a video of our simulator in action. And you'll see in the lower left the view of third-person view of the vehicle. And in the upper right, you'll see the pedestrian point of view. And so here you'll see the pedestrian walking across the road. And the vehicle moving up. Here's the view of the pedestrian. It's a little choppy, but now you can see the pedestrian walking back again and the vehicle crossing the intersection. Yeah, unfortunately, it's playing choppy through the interface, but actually it's quite smooth in reality. So one of the intrinsic problems with connected pedestrian and driving simulators is that cars are fast and people are slow. So when a car drives by, it moves a great distance, and the pedestrian is essentially confined to a single intersection. And so how can you take in a natural experiment and have some ecological validity and have the pedestrian and the driver interact more than at one intersection? There are several ways that people have looked at doing this. One is to restart the simulation each time. So after a single encounter, you just stop the simulation, reposition the driver and the vehicle, and restart the simulation again. The difficulty with that is it leads to this break in the simulation that seems to be artificial to the participants and has less continuity of experience. The second way to do this is try to do some clever routing of the driver. And so make the driver follow a route that will bring them back to the pedestrian's intersection over and over and over again. The challenge there is trying not to, that involves lots of turns. And in general, we don't like to do lots of turns in simulation experiments. And it still takes time to get back there again. The last way that we experimented with in our simulator was to teleport the pedestrian. So after a single encounter, the pedestrian is teleported to another intersection down the block, and the pedestrian will then see the vehicle approaching the intersection again and again and again as you teleport to each subsequent intersection. One of the concerns with that is the disruption that it caused to have your visual display change abruptly for the pedestrian. And the way we tried to ameliorate that was to have the pedestrian look straight ahead, give them a shot clock that tells them that the change is coming, and then make the views as similar as possible. So when they looked ahead and moved to the next intersection, we try to fix their viewpoints so they see as little change as possible. So the combination of that more smooth transition of the notification seemed to help and didn't seem to feel too uncomfortable, at least in our anecdotal experience. Next slide, please. Kelvin?
Sorry, my apologies. I was muted. Uh, I was saying that one of the benefits of this project is it allows us to actually study how we can use uh, non-traditional driving simulation technologies like Unity to do distributed simulation. And one of the other aspects that we wanted to explore with this project is the integration of perhaps Unity and an existing driving simulation platform, or specifically a component of a driving simulation platform. At the University of Wisconsin-Madison, we have an RTI-based driving simulator that is a full vehicle cabin. And we want to see how we can actually make Unity talk to RTI, or more specifically, have Unity listen for what RTI is saying. So just as a demonstration, just as a demo project, what we did is that we actually took our RTI simulator and we added a module to it that will basically stream all the data coming from the simulator, such as steering wheel position, gas and brake pedal position, as well as X, Y, and Z coordinates over UDP. And then we created a module on Unity that will listen for data over UDP. And earlier in the presentation, I mentioned that we separated the control for the steering wheel from the Unity environment. We created our own control system. And this is why we did it, because now the way we design our Unity simulator, that Unity simulator can actually listen for position data, speed, steering, gas pedal from an external data source, such as an RTI simulator. And just to demonstrate this in a very crude and very basic way, this was on the early stages of the project, just to prove our point, we took what you see in here. You're going to see a video of a Unity world shown on the screen here, and this vehicle cabin here is running just the RTI software. And what you see on the video is that the person in the cabin is actually using the RTI cabin, but what's projected on the screen is actually the Unity game engine. So we were able to connect that RTI vehicle cabin to the Unity game engine. For testing purposes, what we did is we have two separate worlds, and we just had like a flat world on the RTI side and the non-flat world on the Unity side. But if we wanted to, we can actually have those two physical worlds be the same and have Unity just listen for where it needs to be. One of the capabilities that we added to the driving simulator system was actually having Unity operate in a playback mode, in which it just listens for, hey, here's where the camera should be, and we can get those positions from an RTI system or any other advanced driving simulation platform. In terms of future work, one of the things that we learned with this project is that Unity provides a lot of flexibility. Now, as Joe mentioned, a lot of times we have to put things together from scratch, and that does present a challenge, but it is it's very flexible compared to other simulation platforms. For example, one of the projects that we submitted as a proposal for collaboration is basically using this Unity platform to study the effect of remote driving. And the reason that we can do that is because the system, the way that it was created, allows us to listen for remote control data or for steering, vehicle, position, gas pedal, all that stuff over the network. So there's nothing stopping us from actually using this to study how you can operate a vehicle remotely, sort of in a drone-like approach, but for vehicles. And that's one of the things that we're looking forward to doing in the future. Also, because of the way that the Unity driving simulator was created and the modularity of it, it is possible for us to actually create a vehicle cabin that sends the necessary data and receives data from Unity without having to deal with the integrated tools that Unity has, which are more targeted towards the traditional controls that are used for gaming. So we could, in theory, wire an entire vehicle cabin, such as the one that we have on our RTI simulator, to our Unity driving simulator. And that's it on our end. If you have any questions, we'll open it for questions now.
We already have a question on the chat. So the first question, I can answer the first question. So our pedestrian is physically walking because the head-mounted display that they are wearing is HTC Vive, and HTC Vive would directly come with the room size tracking. So they can just directly walk across the street in a physical world without using a treadmill.
So I think the second question, I can answer that. Let me read it just for the benefit of everyone. Was the Unity RTI mashup also over a remote network or local? What was the visual other lag? It was basically a local network. We just ran Unity in the driving simulator network. There was basically no lag when you run it on a local network. Really, the lags we have seen are like a few milliseconds. But that was running local, not over the network, like in between Wisconsin and Iowa. Yes, for the Unity RTI mashup, all of the control dynamics of the vehicle were still being run through SimCreator. So that allows us to basically use the RTI vehicle cabin and SimCreator as the physics engine for Unity. So let me be specific. RTI was running a physics engine at the same time that Unity was running a physics engine. In our end, for our test, what we did is just have RTI driving on a flat platform and Unity having their simple physics engine. Later in the process, and this is not shown in the video, we added capabilities to Unity to basically receive just X and Y coordinates from any other system, which means that we can just delegate the physics to an RTI system and have Unity basically be a player.
So get time to collision, do you mean like data processing? If you mean time to collision is the data processing, it's kind of like the Unity programming is similar like to other simulations. We can just use the C# to record all the moving objects. And after the simulation is done, we can put the data into analyzing and figure out the time to collision.
Also, we did a little bit of a test for those sensors, and in Unity on our driving side of things, we added some colliders, just like you would do with any other simulation platform, in which we say, okay, based on the speed, based on the position, start the moving of this vehicle based on this factor. So that could be time to collision. I have another question here, I think related to RTI. Were you able to use other modules of RTI simulator, like scenario creation or ambient traffic with Unity? No, we didn't try that, and that was kind of a design decision from the beginning. We didn't want to have to deal with mixing those two environments at that level. All we were really interested was the physics of that RTI provides, as well as the vehicle cabin itself. So we just added a module to RTI that just streams data over the network, and that was it.
So for the Unity capability, like we didn't really do it, but the Unity is able to create some of the other things, just like regular games, because of the gaming platform. If you see stuff that you can see in the games, like the ambient traffic, you can still create it with Unity.
I have another question here. Let me read it for everyone's benefit. I guess the next step will be to look at distributed Unity RTI network. So a Unity pedestrian interacting with an RTI driver in their respective worlds. How non-trivial does that seem in your opinion? To be honest, I wouldn't even know where to start to answer that question. I have an understanding of how RTI handles like vehicles. At least it will involve a lot of JavaScript. That will be my opinion, because you will have to basically, if we want to do it just a very raw method, not by basically not bringing in any changes to the RTI code. The only way that comes to my head of how to do that will be to have a pedestrian in the RTI environment that listens for position data on UDP, but that position data, I don't think, unless things have changed, that you can set the XY coordinate of a pedestrian. All you can do is set perhaps the speed. So we could do an approximation by just having a module that, instead of sending data over UDP, listens for data over UDP, and then the pedestrian queries the speed based on the UDP data, and then sends the pedestrian, to a particular marker and initiates a transition. So that's again, not sure I can answer that question really, but that's my best take of it.
All right. Well, thank you everyone for the excellent questions, and thank you for presenters for the great presentation. It looks like the questions have slowed down, so I think this will be a good place to end it. I want to thank everyone for joining today. As usual, we will get this webinar up on our SaferSim YouTube channel within the next week. And then look out for our future announcements for the next webinar, which will be Tuesday, February 26th. That is a presentation from the University of Central Florida, so we hope you are able to make it there too. Thank you, everyone.